All right, so let's begin today. If you remember in the last lecture, we finished aldehydes and ketones, and I kind of started transitioning, at least giving you kind of an outline of what we would be doing the rest of the semester. Today, we're going to talk about carboxylic acids. We may totally finish our discussion of it in this one lecture, I'm not sure. But there's not a lot of material to cover with carboxylic acids because there are not as many reactions that they undergo compared to when we get to the interconversion between all the carboxylic acid derivatives, all of those reactions that we're going to study. And by the way, we're in chapter 9 now for the most part. That's where the carboxylic acid derivative material is, so you know where to look in the textbook. So with carboxylic acids, it's a new functional group. So we'll do like we normally do. We'll talk about nomenclature first, and then we'll move into how to prepare carboxylic acids. And the good thing is we already know a lot of ways of doing that, so it's going to be a review. And then we're going to talk about the few reactions that the carboxylic acids will undergo. So let's start with nomenclature. Now you'll notice in the nomenclature of carboxylic acids, there's two things that you'll notice. First, the nomenclature is very similar to that of aldehydes because it's a terminal functionality. You can only find a carboxylic acid on the terminus of a molecule, and so that kind of governs its nomenclature. It's always going to be that carbonyl carbon's always going to be 1, etc. And then if you have a ringed system, we need to have a name for it as a substituent because the carboxylic acid itself cannot be part of a ring because it's a terminal functionality. Okay, so you're going to see both those elements. So let's start with open chain carboxylic acids and the rules that pertain to that nomenclature. Okay, so what you're going to do is it's named by replacing the E ending of the corresponding alkane with, okay, and this is important, it's oic acid. Those are two words, oic acid. Okay, so again, name derived from the alkane. And then the second thing, you're going to start counting at the carbonyl carbon, which is exactly what we saw with an aldehyde. It's a terminal functionality, so you're going to start numbering there. That makes perfect sense, okay? And so, it goes without saying then that the longest continuous chain, the parent for naming the carboxylic acid is going to be, the chain that contains that carboxyl group at its terminus, all right? And so let's do a few examples. Okay, so what will we do here? Longest continuous chain. You can see we can go in either direction here because it's symmetric. So right straight across, start numbering at the carbonyl carbon, and then we're going to name this like it were an alkane and drop the E and add oic acid. So if it were an alkane, what would this be? For methyl pentane, right? But since it's an acid, we drop the E and we add oic space acid. Okay, so 4-methylpentanoic acid. Okay, how about this one? You can see that's pretty straightforward. So what about throwing you a little curve like this? Let's put 2 carboxyl groups on this. Okay, so now it doesn't matter which end we start numbering on. This is the longest continuous chain. I'm going to number this as the starting point. Okay, so there are 5 carbons there. If this were an alkane, it would be what? pentane. But now I have 2 carboxyl groups. Now, numbering is not important here because the carboxylic acid always has to be on the terminus, right? So you know that it's going to be, in the case of a pentane, it's going to be at the 1 and the 5 position. There's no other way to do it. But how am I going to indicate that there are 2 carboxyl groups here? Normally I would just add oic acid, but since there are 2, I'm going to say dioic acid. Okay? What about if your carboxyl group has to be named as a substituent? And that would be a case like this. Well, let's look at that first in the rule. If you have to name it as a substituent, it's going to be a situation like this, where your carboxyl group is, attached to a ring. So it can no longer be the parent because it can't be part of that ring because it's a terminal functionality. And let's just put in a couple of other functionalities there. And so how would we name this now that it would have to be named as a substituent? Well, the rule is that basically you're going to use a different suffix. And so again, just like an aldehyde, you're naming it as a substituent, but it ends up being a suffix that you add to the end of the molecule. And the suffix, now get this, is going to be really hard to remember. Carboxylic acid. That is the suffix that you add to the end. Okay? When you start numbering, the carbon to which the C double bond OH is attached is always numbered 1. Okay? Always 1. And so if we were to name this compound, and I've kind of written around it, but if we're going to name that compound, what would we do? Well, we'd start numbering here, and then what we know, we can go in 2 directions, but what do you think you're going to do as far as numbering? You're going to number where the double bond has the lowest number, right? And so we're going to number around that way. And so therefore this is what? 5 hydroxy, because that's the name for this as a substituent. And then what else? It's going to be 6-membered ring, so cyclohexane would be what it was if it were a cycloalkane, but it's an ene, right? Because it has a double bond, so cyclohexene. Okay. And then because I'm going to add, normally you drop the E, but I'm going to add this suffix carboxylic acid. So I don't want to put an N and a C together, so I'm going to leave the E there. And I'm just going to add carboxylic acid. So it's a 5-hydroxy cyclohexene carboxylic acid. Is everything there that needs to be there? No, because I need to identify where the double bond is. So here I need to insert my 2 that identifies where the double bond is. All right? And so that's how you would name it as a substituent. Now, carboxylic acids were some of the first functionalities that were discovered. So you have a lot of trivial names associated with carboxylic acids. Okay? And so there are a few I want you to know. Trivial carboxylic acid names. Some of them you will have heard before. Okay? Now the first thing is the C1 to C4 carboxylic acids have, trivial names that we use all the time for them. C1 is formic acid, and we write C1, C2, C3, C4. Formic acid is where you have 1 acetic acid. You certainly heard of that. That's where it has 2 carbons. And then you go to propanoic and then you go to butyric. And butyric acid is famous for its really bad smell. It smells like gym socks. Or, you know when you're walking across campus when the female ginkgo is dropping her fruit on the sidewalk by Munger, and people are stepping on that fruit and it has that really pungent odor. That's what butyric acid smells like. Okay, so those C1 through C4, you have these trivial names. Okay, but then there are also some trivial names for some more complex that I expect you to know. And the first few are dioic acids. In other words, compounds that would have two carboxyl groups. The simplest one you can draw is this, which is oxalic acid. And then you can insert a CH2 spacer between your two carboxyl groups like this. And the trivial name for this is malonic acid. And then if you put two CH2 spacers in between your two carboxyl groups, you get something that all of us have seen, succinic acid. Okay, and then those are your common diacids. And then you have your aromatic. This we know we call benzoic. That is in fact a trivial name, as we saw when we were talking about nomenclature. And then we can have the aromatic ring with two carboxyl groups off of it. And you may not remember this, but we did this at the beginning of the semester. It was one of the compounds we used when we did that, doing melting points and TLCs and all this. It's called, I have to make sure I'm spelling it right, phthalic acid. And this happens to be orthophthalic acid, but you could also have metaphthalic acid or paraphthalic acid, depending on how these two carboxyl groups are associated on the ring. Okay, so these are the trivial carboxylic acid names I expect you to know. Okay, and so that brings us to preparation of carboxylic acids, because we want to make sure we know how to prepare them before we proceed on to reactions. So preparation of carboxylic acids. Now again, I was telling you earlier, the good thing about this is review. We know several ways of making carboxylic acids already. So I'm just going to go ahead and list the ways we know. Okay, the first are by oxidations. First of these was if you had an alkyl benzene. So you have an alkyl benzene, and I'm just going to use the generic because this is review. Remember, if we had a benzene ring and there's an alkyl group attached, we could treat this with potassium permanganate under neutral conditions, and you would always oxidize to the benzoic acid. Okay, and remember, this R group had to be either primary or secondary. If there was if this was tertiary and there was no benzylic proton, then the oxidation wouldn't work. So that's review. Just make sure you go back and look at that. Okay, so that is really under the category of oxidation. It's an oxidative cleavage, right? Okay, and so that should ring a bell. Oxidative cleavage, because we can also do oxidative cleavage on alkenes. We saw that last semester. And remember, we were reminded of this when we were talking about preparation of aldehydes. And that is, if you have an alkene like this, you can do the oxidative cleavage, again, using potassium permanganate, same reagent as above. when you're at neutral or acidic conditions. Remember, it can't be basic. Basic gave the hydroxylation instead of the oxidative cleavage. So it has to be neutral or acidic conditions. You do the cleavage here. And so remember, in the cleavage, if you have two R groups attached to your alkene carbon, you end up with a ketone. But if you have a vinylic H, so in other words, an H attached to the alkene carbon, if you have that under potassium permanganate conditions, then when you do the cleavage, you will cleave to the carboxylic acid. Okay? The vinylic hydrogen, you oxidize all the way to the carboxylic acid if you're using permanganate. Now, just as an aside, I'm not going to write anything. If you had the same alkene and you did a cleavage, but you didn't want to get the carboxylic acid, you could also get the aldehyde. Remember, we reviewed that when we did ketones and aldehydes, and that's where you use ozone instead of permanganate. Different result. Okay, but that's another way of making a carboxylic acid by oxidative cleavage of an alkene. Okay. You can also oxidize alcohols. If you have a primary alcohol, you can oxidize that all the way up to the carboxylic acid. That was material that was on the second exam, right? But you can also, remember I emphasized, you can also oxidize an aldehyde then completely to carboxylic acid, and you're using the same reagents basically. So if you have a primary alcohol and you treat it with Jones's reagent, remember, which is chromium trioxide, basically in sulfuric acid and water, Jones's reagent, it will oxidize this all the way up to the carboxylic acid. Okay, and oops, I added an extra carbon there. Okay, now you could also remember, just write the word Jones's reagent here. You don't have to write out chromium trioxide, sulfuric acid. That the assumption is that that's, if you write Jones's reagent, it's the same thing. All right, but remember, if we already had an aldehyde like this, then we can use the same reagent. If we use Jones's reagent, we'll take that aldehyde and oxidize it all the way to the carboxylic acid. Right? Because I'm just going an additional oxidation state. Okay, so both of these things are reviewed. But I do want to show you one additional reagent that works at oxidizing an aldehyde to the carboxylic acid. And it has biological applications, because this is something, I don't know whether you've talked about the Tollens test in biochem or in one of your biology courses. It's a way of checking for reducing sugars. You know, you're looking for the aldehyde functionality, so it's kind of like a qualitative test for the presence of an aldehyde, and it's using a silver reagent, usually like silver oxide, in ammonia. This is called Tollens reagent, which also leads to it's called the Tollens test, because you're testing for aldehydes. And what happens is it will reduce an aldehyde to carboxylic acid. It doesn't reduce primary alcohols, okay? Just aldehydes to acids. And I'm just showing that because, you know, it is a reaction that's used a lot in the laboratory to test, you know, sugars to see if they have the aldehydic functionality on them. And the other interesting thing about this reaction, I've done it before, it's kind of neat. It's almost like, you know, something you would expect to be done in medieval times to prove that you can actually make precious metals. Because when you do this oxidation, the silver gets reduced. and it becomes metallic silver. So when you do this reaction, the inside surface of your glassware actually gets coated with silver. It's pretty neat. All right, so that's just a bonus reaction for you to look at. All right, so those are some review ways of making carboxylic acids. And then another one we also have seen before, hydrolysis of nitriles. And remember, this was really under the category of a synthetic utility reaction, one of those reactions I show you because we're focusing on synthesis. So we learn a transformation, then I say, oh, by the way, you can convert that functionality to something else that might be useful in synthesis. So we talked about this hydrolysis of a nitrile, maybe more than once. And so that is where you have this nitrile functionality, which we said, is kind of included in carboxylic acid derivative functionalities because this nitrile behaves very much like a carbonyl. And so when we treat this with aqueous acid, it'll do hydrolysis. And when you hydrolyze it, you actually form the carboxylic acid. Okay? All right. And just as an aside here, do we know how to make a nitrile to then be able to hydrolyze it to get the carboxylic acid? Yeah, remember you make these just simply with SN2 reactions. If you have an alkyl halide, you can always easily make the nitrile by SN2, just react it with, sodium or HCN. Any of those will work, and you end up forming the nitrile that can then be hydrolyzed. Okay? Now for a new reaction, in a sense. It's not a new reagent, just a new application of it, and that is carboxylation of a Grignard reagent. So Grignard reagents we've been using a lot, and carboxylation means you're adding CO2. You're adding that carboxyl group. You're adding it, okay? And so you're not transforming it from something else. You're actually adding CO2. So you're going to be adding a carbon to your molecule, as we'll see. So in the sequence of things, and let's do simple case first, let's take bromobenzene, and we're going to convert that, reacting it with magnesium metal, remember, in ether, and that'll form the Grignard reagent, where the magnesium is just being inserted. And once you have that Grignard reagent, then what we're going to do is we're going to add CO2, okay, followed by an acid workup. So this is, standard reaction procedure that we've been doing, reagent, acid workup. And the result of this is going to be the addition of the carboxyl group to give the carboxylic acid or benzoic acid. And notice I have 6 carbons here. Those carbons in the ring, I have 7 carbons here. So you're adding a carbon. When that CO2 adds to the molecule, you're increasing the number of carbons by 1. And so to emphasize that, let's look at a different example. Let's look at an acyclic or open chain. 3, let's use 4 carbons, and let's have the chloro form of this. So I'm first going to treat this with magnesium and ether, and that's going to form the Grignard. Okay, and then I take that and I treat it with CO2, followed by an aqueous workup, and now watch this. I had 4 carbons in my Grignard, and now I have 5 carbons because I've added this. This comes from the CO2. All right. Now we're going to look at this mechanistically in a second, but I want to talk experimentally about it, since we don't have the pleasure of actually being in the lab, this latter part of the semester because of the virus. I want to talk a little bit about how would you carry out this reaction, because it's kind of interesting. I think I told you on making Grignards, what you basically do is you get a glass column and you fill it with magnesium turnings. It's just magnesium metal. It's almost like you can imagine if you drilled through a piece of magnesium metal and it has the little, slivers of metal that would come up as you're drilling. That's what turnings look like. So you have magnesium turnings in this glass column, and then you put a solution of your alkyl halide in ether. You run that through the magnesium column. And as it runs through the magnesium, it's being converted into the Grignard reagent. And then you can just have some collection vessel at the bottom of the column, and your Grignard is just dropping into that vessel. Okay, so that's how you form this. And then all you have to do is go to ESA and say, I want some dry ice, which is basically CO2. And you just throw little pieces of dry ice into that reaction vessel, and it will react with the Grignard, and you will form that carboxylic acid. So it's a really simple reaction to do. Okay, mechanistically, how is this working? Well, by now, we've really learned all the mechanisms. It's just applying them to those situations. I mean, I don't want to insult you by, showing you something that you can probably figure out. So let's just work through it. You have a Grignard, and let's just use the generic form. And we know the Grignard is a carbon nucleophile, right? So that's going to be R minus. And if I'm reacting it with CO2, this is the structure of CO2, right? So nucleophile is going to react where? It's going to react with the electrophilic site of the CO2, which is basically here, because that carbon is like doubly carbonyl. It has two double bond O's on it. So it is, it's got that partial positive charge character. It's electrophilic, so my nucleophile is going to react right at that center. When it does, it's going to break one of the pi bonds and move the electrons out to the oxygen. It doesn't matter which of these pi bonds it breaks, right, because this is symmetric. And so the result of that is you have added your R group to that carbonyl carbon here of the CO2, push these electrons out, and now you have your magnesium as the counter ion. And then when you do the, I'm going to do it like this, when you do your H3O plus your acid workup, all you're basically doing is protonating that to give the carboxylic acid, and then you're giving back water. Okay? So very simple and straightforward. So now we've seen, several review reactions that prepare the carboxylic acid, and now we've seen one new one that, is using a reagent we know. Okay? Now the important thing to remember when you're doing this reaction, you're adding a carbon. Okay? This R group had a certain number of carbons. When I added the carboxyl group, I've increased the number of carbons in the molecule by 1. That's important to remember. When you're carrying out a synthesis, you're adding a carbon when you do that carboxylation. Okay? So those are all the ways of preparing carboxylic acid. So if we're going to do a synthesis, now we know how to make the carboxylic acid, and now we're to the point of talking about what can we do with the carboxylic acid once we form it. So reactions of carboxylic acids. Okay, and so we're going to talk about several things we can do with them. So I'm going to do what I did with alcohols. I'm going to draw kind of a generic carboxylic acid. And let's talk about what reactions we can do with this. Okay, the first is an alpha substitution. And we'll see if we actually get to this reaction. It depends. But remember, we talked about the fact that the the carbon that's once removed from the carbonyl is called the alpha carbon. So if you're doing an alpha substitution reaction, that means that you're substituting a nucleophile, not at the carbonyl, but at the alpha position. Okay, so that's one reaction that carboxylic acids will undergo. They also will undergo a decarboxylation. So it's not a carboxylation, it's a decarboxylation. So that's actually the opposite of the reaction to prepare carboxylic acids that we just talked about. Okay, and so that means that I'm basically, what's going to happen here? I'm going to actually lose CO2. So I'm going to lose my carboxy group, and in the process of doing that, in the reaction that we talk about, you're going to have a halide replacing it. Okay, so it's a loss of CO2, decarboxylation, right? Then you can just have a simple reaction that leads or changes the reactivity of it, and that is just deprotonation. And that's really a preparation for other reactions, but then we can reduce this, and this is a reaction we've already talked about, but we'll revisit it, right? Because when you reduce this, what happens? You reduce it to the alcohol, right? And then we're also going to talk about the most important reaction that the carboxylic acid derivatives undergo, and that's nucleophilic acyl substitution. And remember, we talked about that mechanistically and otherwise already. And that's basically where you're going to react this with some nucleophile, and that nucleophile is going to substitute for the OH. Okay? And that would be nucleophilic acyl substitution. So we're going to address all of these, okay, in turn. We're not necessarily going to do them in any particular order, because I think we're going to start talking about reductions first, okay, because that's kind of a review. We've already talked about that. So let's say you want to reduce a carboxylic acid. To reduce it, remember, we're going to use reducing agents. And we talked about reducing agents in the terms of carbonyls when we were talking about preparation of alcohols, right? We talked about how sodium borohydride will reduce ketones and aldehydes, and we talked about the fact that lithium aluminum hydride will reduce ketones, aldehydes, and carboxylic acids and their derivatives, right? So we already know LAH is a reducing agent that will work with carboxylic acids. There is another one very commonly used, which is just borane. And we've seen borane in a different application when we were talking about what particular thing, hydration of alkenes. And you had oxymercuration, and you also had hydroboration. Remember, that used borane as a reagent, but here it's serving a different function. It'll reduce carboxylic acids. But just to remind you off to the side here, I'm actually going to write not sodium borohydride. Sodium borohydride, remember, is not a strong enough reducer to reduce carboxylic acids or their derivatives. So we're basically talking about these two reducing agents. Okay, so let's look at an example of this, which you can think about. This would be how it would look on your flashcard. And let's use this example. So you have your carboxylic acid, and we're going to react it with LAH. And remember, what did we always do after we reacted with this reducing agent? We always did an aqueous acid workup. So that's the kind of thing you would see in a reaction section of a test, something you can put on your flashcard. This is the actual reagents on the arrow. And when you reduce this, remember, LAH has no effect on double bonds. We talked about that. And so I'm going to reduce this basically to the alcohol. So it would end up being reduced like this. All right, very straightforward, nothing unusual about that. But that's how LAH works. We've seen that. But borane, let's look at how that would work. So I have my carboxylic acid, and I'm not going to make benzoic acid. I'm going to put a spacer on there just for fun. Put a nitro group there. And I'm going to react this with BH3. Okay? And then I'm going to follow that with the aqueous workup. Now, as you remember from hydroboration, when you use borane, you typically have THF as the solvent. So I'll go ahead and put that there. And so this is going to be the same kind of reduction we saw with LAH, right? It's just going to reduce this to an alcohol. So your product is going to be this. Nothing happens to the NO2. It's not reduced. That's your carboxylic acid is. Okay? Now, that's something that's important about borane. Borane very selectively reduces carboxylic acids. So in the presence of nitro groups, of ketones, of aldehydes, of esters, if you have other carbonyl functionalities in there, borane typically is specific for a carboxylic acid. And so you often see that used as a reducing agent for acid groups. All right? Okay, next reaction is the decarboxylation. Okay? And remember, the decarboxylation was what we said was kind of the reverse of the Grignard with CO2, because that was adding a carboxyl group. Now I'm removing it. Okay? And the reaction that affords the decarboxylation is named after someone. Huns-Diecker reaction. Hunsdiecker. Huns-Diecker reaction. And it's basically the loss of CO2 from your molecule, which means that you're losing your carboxylic acid functionality, but you're losing CO2, and CO2 is a gas, and you're losing a carbon from your molecule. So when you're doing synthesis, you have to remember, yes, I'm getting rid of the carboxyl functionality, but I'm also losing a carbon from my structure, okay? And so what are the conditions? And by the way, yeah, this reaction is named after somebody. It used to be if you came up with a new reaction, they would name it after you. They don't do that anymore. Conditions for the reaction. It requires the use of a heavy metal, which is not the music. It's actually something like mercury, silver, or plumbum, which is lead. So you're using a heavy metal, but you also are using bromine or iodine. Okay, so you're using both of these reagents. Okay, they can be used interchangeably and they all work pretty well. So what would the reaction look like, and what would you put on your flashcard to demonstrate these conditions? Well, let's look at an example. I'm going to put 4 carbons and then my carboxylic acid group. Okay, you're going to treat it with a heavy metal, and let's use mercury, and it's usually the oxide that you're using. So mercury oxide, and then bromine, Br2, and then a solvent, which is often carbon tetrachloride. So this would be what you'd put on your flashcard as the conditions for the Huns-Diecker reaction. Heavy metal, bromine or iodine, and then the solvent. Okay? And the result of that is going to be the decarboxylation. So that means that I'm losing the O2H, but I'm losing it as CO2. And the halide is replacing it. And so I'm going to form this alkyl halide minus one carbon, and then I'm also going to have CO2 forming, which is a gas. Okay? That is what forms. Boy, this looks like it might be a fun mechanism. So let's look at that. Mechanism. Well, this mechanism involves several steps, and we don't electron push completely through all of it. Okay, so let's take it stepwise. First thing that happens when you take your carboxylic acid and you put it in the presence of a heavy metal, it's going to immediately form this intermediate, where basically the metal is going to replace the H of the carboxyl groups. I'm not even showing that. That's just what happens. So this could be mercury, silver, or lead. Okay, and this is actually called a carboxylate because you basically have a minus charge there. It's kind of salt-like. And since it's mercury I'm using, it's mercuric carboxylate, but it could, depending on what other metal you're using, you would just insert that metal name in front. Okay, once that forms, then your halide reacts with this, and you form this, which is a acyl hypobromite. And it, because we're using bromine, but it's also giving you this metal salt. Okay, so all of this kind of happens once you put the carboxylic acid in the presence of the heavy metal and the halide. It spontaneously gives you this compound. We're not doing electron pushing there. Okay, it's not really interesting because you can just see it's just like forms of salt. But let's start at this point right there, because this is where the mechanism gets interesting. Because we're going from a polar type reaction to a radical reaction, which you might have suspected when you saw, how often do you see an O to halide bond? Not very often. So if it's a radical process, we need an initiation step. And this is the initiation step. And basically what's going to happen is you're going to homolytically cleave this O to halide, in this case bromine bond, okay, homolytically, because this is a radical reaction. And when you do that, you're going to form these two radicals, okay? Once that forms, you enter the propagation steps. Okay, so I'm going to draw my carboxyl radical that has formed, right? And then it's going to undergo a spontaneous series of homolytic formations and cleavages, because this one electron is going to move in, okay? While this bond is cleaving, that electron is going to move in, and then another electron is going to move out to the R. And so that's going to give me the alkyl radical. You see that? Because I'm homolytically cleaving this bond, I'm homogenically forming this bond, breaking that single bond, forming a double bond. And so what does that basically give me then? It gives me CO2, which is lost as a gas. Okay, so that's the initial step. Well, I've formed this radical, so I'll carry this down there. That's going to react with another of these acyl hypobromite. Okay, and so that's going to come in, and you can imagine you're going to homolytically cleave this bond, right? And so one electron from that bond is going to come over here
to homogenically form a bond between the R and the bromine. The other electron is going to move out to form that carboxyl radical. And so the result of this is I've formed a bond between that alkyl group and the bromine, but I've also formed what? This radical. This radical then is here and can spontaneously decarboxylate and continue the process. So remember, this is what we call a chain reaction. All right? So that's how this reaction occurs. Initially forming the acyl hypobromite, and then that undergoes the spontaneous decarboxylation, giving the R radical that then continues this process. All right? And so that's everything we need to know about preparation of carboxylic acids and reactions of carboxylic acids. Isn't that great? That's the whole, everything about carboxylic acids. And that's going to allow us now to start talking about carboxylic acid derivatives. And so next time we get together, again, I think I prepared you for this last time, we are going to start talking about the carboxylic acid derivatives, and we talk about them kind of all at once. So next time we're going to do nomenclature, and it may be a full hour of nomenclature because there's a lot of it. Very similar rules for how to name it. A lot of it is just changing suffixes, as you would imagine, but a lot of rules to go over. So next time be prepared to do a lot of writing. Okay, and then we'll move into preparation and reactions. And what we're going to find is when we talk about preparation of each of the carboxylic acid derivatives, then when we get to their reactions, we're also then talking about preparation for the other carboxylic acid derivatives. And gosh, see, I don't have enough room to do my normal walking around and waving my arms. I have to stay in this little confined space. But we're going to talk about the fact that reactions and preparation reactions are all become kind of repetitive. And so it'll seem like we're being introduced to a lot of reactions, but we're actually, there's redundancy as we go through it. And you'll be aware of that as we proceed. So I'm going to go ahead and stop. We're a little short of 50 minutes by my clock, but we've covered the whole chapter on carboxylic acids, which I promised you we would. And so we're going to go ahead and stop here. And then in the next lecture, we'll pick up with carboxylic acid derivatives.